It's what you do with a parameterization that I'm most interested in. So this is something that we haven't talked about in quite a while in class. So as Aaron discovered, if you missed that day, then there's a gap that needs to be filled. So what I'm going to talk about for each problem where it applies is what are the applicable formulas for that problem. So the one in this case is when you're integrating a scalar function along a curve. This is kind of like a formula for arc length. That you substitute your parameterization, and then you have the derivatives of your parameterization, x prime of t squared plus y prime of t squared dt. So curve has these parametric equations. And already I'm beginning to not like this marker. Okay, well, I'll use it for this problem and then I'll switch. So this is a formula that applies so when you're integrating a scalar function over a curve or surface, there's always going to be some nasty square root expression involved, unfortunately. But I think this is the only problem on the exam where that sort of thing comes up. Now, how do you parameterize? Now, in most cases, unfortunately, there's no systematic way of doing it, unless if a curve is described to you by y being a function of x, then there is a systematic way to do it. You just use x is equal to t, and x runs from a to b, so 0 to 1 in this case. And then y is equal to f of t. So then this will become square root of 1 plus f prime of t squared. So in a special case where if a curve is a graph of a function, then it reduces to that. And fortunately, that applies here. So, okay. So that's how you're going to parameterize this curve. Y is equal to x squared. X runs from 0 to 1. You'll apply this, so your f of t will be t squared, and then you get an integral that is, unlike certain past integrals, pretty reasonable to evaluate. All right. So, all good on the approach to that one?
Yeah. I've already done this one.
Yep. Yeah. So yeah, I guess I can do that too.
Yeah.
Yeah, it's a perfect one for lulling into a false sense of security.
Yeah, I knew I wasn't gonna be like that.
Well, good.
You have to give people a chance to get one.
That's the idea. Yeah. Throw up a bone.
May not let them pass the class, but
At least you get 10 out of 100.
maybe partial 10 out
Yeah,
of
because you're going to get closer to 110 out of 100 than 10 out of 100. Oh, I have to find all the sheets where I've written all the attendance bonus points.
I have 10 right now.
I'm sure you have points for being here.
No, I know you have 6.
I thought I'd try.
I think I have 6 too, don't I?
Yeah.
Yes, because both of you have shown up every time since I started doing that, as have a fair number of the other people who are benefiting. Okay.
I always think that guy next to me drops the class because he'll be gone for 2 weeks, and then he comes back for like a day. And he's gone for 2 more weeks, and he comes back for 1 day.
Yeah.
I don't even think he's in this class. He just shows up.
Well, too bad he's on my list and I had to give him a grade.
Oh man.
Oops. Okay. Next one. So now we have this curve. We have an ellipse. 4 4x squared plus 9y squared equals 36.
What? You can get all letters?
Okay. Now, because this is a closed curve, there are two ways to do this problem. Now, I'm going to talk about one way to do it that it would apply even if this was not a closed curve. And so it would be a good exercise anyway. If we go ahead and parameterize this, then this one's a little more difficult to parameterize because it's not y being a function of x. However, this equation is kind of circle-like because you have constant times x squared plus constant times y squared is equal to another constant. So it's like x squared plus y squared is equal to r squared, where x is r cosine t, y equals r sine t, and that is counterclockwise. T runs from 0 to 2 pi. So it's going to be kind of like that, but now you got to take into account these constants, the 4 and the 9. So for instance, what you could do is we can call this a squared. You call this b squared is equal to 6 squared. So you can think of it as a, which is equal to 2x, is also going to be equal to 6 cosine t. B, which is 3y, is going to be equal to 6 sine t. So the reason why I'm putting the 6 in here is because we have a 6 squared on the other side. So this is what's going to go right here. Here, just associating these, a squared is 4x squared, so that tells me that a is equal to 2x, and b is equal to 3y. So now you have a parameterization. X is 3 cosine t, y is equal to 2 sine t. And t goes from 0 to 2 pi. And then what you would do is, this would be the integral from 0 to 2 pi of y prime of t I'll just label everything. Sorry, x prime of t. So x is 3 cosine t, x prime is minus 3 sine t, plus x plus y squared times dy, that's y prime of t.
Wait, so is the first one x prime of t?
Yes. And then now we have y prime of t over here, so that's 2 cosine t. That's y prime of t. And this is x of t plus y of t squared dt. All right. So, yes, so then you can work that out and try integrating that. And now this is an approach that you can take even if C is not a closed curve. For instance, suppose we were doing half the ellipse, like the upper half. Then t would just run from 0 to pi, and those would be your limits, but everything else would be exactly the same. Now, but because this is a closed curve, there is another far, far easier way to do this problem.
I hope it's what I do.
Green's theorem applies. That isn't what he did?
No, I parameterize for